Welcome to this walkthrough of problem number 1054, distant barcodes. In this session, we'll break down the problem, explore different approaches, and analyze their efficiency. By the end, you'll have a clear understanding of how to tackle this problem effectively. Let's get started. This problem involves rearranging barcodes in a way that no two adjacent barcodes are the same. The barcodes are represented as integers in an array, and our goal is to produce a valid arrangement that satisfies this condition. If there are multiple valid solutions, any one of them is acceptable. For the input, we are provided with a list of integers, each representing a barcode. The output should also be a list of integers, representing one valid rearrangement where adjacent integers are distinct. For instance, if the input barcodes are 1, 1, 1, 2, 2, 3, we need to rearrange them so that no two adjacent integers are the same. Let's look at an example to understand this more clearly. For the input barcodes 1, 1, 1, 2, 2, 3, one possible output is 1, 2, 1, 2, 1, 3. In this arrangement, no two adjacent integers are the same. For example, the first and second elements, 1 and 2, are different, as are 2 and 1 in the next pair. While this is one valid solution, there can be other valid outputs, such as 1, 3, 1, 2, 1, 2, or 2, 1, 2, 1, 3, 1. Any arrangement that meets the condition of having no two adjacent integers be the same is acceptable. Now, consider another example where the input is 7, 7, 7, 8, 5, 5, 5. For the input 7, 7, 7, 8, 5, 5, 5, one valid output is 7, 5, 7, 5, 7, 5, 8. Here, no two adjacent integers are the same, and the condition is satisfied. Other valid outputs could include 5, 7, 5, 7, 5, 8, 7, or 7, 5, 8, 5, 7, 5, 7. The key is that, regardless of the arrangement, adjacent numbers must always be distinct. Another example is when the input is 1, 1, 1, 1, 2, 2, 3, 3. A valid output for this input is 1, 2, 1, 3, 1, 2, 1, 3, where all adjacent barcodes are distinct. Again, other valid outputs may exist as long as the condition is met. Finally, let's go over the constraints and edge cases. The length of the barcodes array can be as small as 1 and as large as 10,000. While each barcode value ranges from 1 to 100,000. It is guaranteed that a valid arrangement is always possible, meaning no input will violate this condition. For edge cases, consider an array where all barcodes are identical, like 5, 5, 5, 5, 5, 5. This would not be a valid input because it's impossible to rearrange these to satisfy the condition. For the smallest input, such as 1, the output would simply be 1, as there's no adjacent barcode to compare. Additionally, for cases with multiple valid arrangements, such as 1, 1, 2, 2, 3, 3, any valid output is acceptable, for example, 1, 2, 1, 3, 2, 3, or 2, 1, 3, 1, 3, 2. To tackle the problem of arranging barcodes such that no two adjacent barcodes are the same, several approaches can be considered. One of the most straightforward methods is the brute force approach, where we generate all possible permutations of the given barcodes and check if any permutation satisfies the condition. While this idea is simple to understand, it is incredibly inefficient. The time complexity is factorial, O(n), because generating all permutations grows exponentially with the size of the input. For larger inputs, like when n is in the range of 10,000, this approach becomes computationally infeasible and is only suitable for very small datasets. Another approach is to use a greedy strategy combined with sorting. Here, we count the frequency of each barcode, sort them by frequency, and then try to place the most frequent barcodes first in alternating positions. While this ensures that the highest frequency barcodes are prioritized, managing these placements to avoid adjacent duplicates becomes tricky. Additional data structures may be needed to handle the placement, which introduces inefficiencies. Sorting alone has a time complexity of O(n) log n, but the additional placement checks make this approach less optimal and harder to implement efficiently. The strategy we ultimately choose to solve this problem efficiently is an optimized greedy approach that leverages a max heap, also known as a priority queue. The key insight here is that the most frequent barcodes should be placed first to minimize the chances of adjacent duplicates. A max heap allows us to dynamically prioritize barcodes based on their frequencies. The approach begins by counting the frequency of each barcode using a hash map. Then, we insert all barcodes into a max heap where the most frequent barcodes can be retrieved efficiently. The placement process involves repeatedly extracting the two most frequent barcodes from the heap and placing them alternately in the result array. After placing a barcode, its frequency is reduced, and it is reinserted into the heap if it still has remaining counts. This ensures that no barcode is placed adjacent to itself. If there is one final barcode left at the end, it is handled as an edge case. The time complexity is efficient. Counting frequencies takes O, n, and heap operations, including insertions and deletions, take O, n log k, where k is the number of unique barcodes. This gives an overall complexity of O, n log k. By prioritizing the most frequent barcodes and leveraging the heap for dynamic reordering, this approach guarantees both efficiency and correctness. In addition to its efficiency, the max heap-based strategy has several advantages that make it the best choice for this problem. First, it handles edge cases effectively, such as when one barcode appears significantly more frequently than others. Sorting alone, as in the earlier greedy counting approach, does not allow for dynamic adjustments based on remaining frequencies. On the other hand, the heap provides the flexibility to reorder priorities dynamically, ensuring that the most frequent barcodes are processed first at every step. By alternating the placement of the two most frequent barcodes, the risk of adjacent duplicates is minimized. When comparing this approach to others, brute force is clearly too slow, with its factorial time complexity making it impractical for large inputs. The greedy counting approach with sorting is faster, but it struggles with the dynamic placement aspect and becomes cumbersome to implement. The optimized heap-based strategy strikes the perfect balance by combining runtime efficiency, O, n log k, with simplicity and clarity in implementation. This makes it the most practical and reliable solution for the distant barcodes problem. In this problem, we are tasked with reorganizing a list of barcodes so that no two adjacent barcodes are the same. If it's not possible to achieve this, we should return an appropriate solution, such as an empty list. The challenge lies in designing an efficient algorithm to handle this scenario, especially when dealing with high-frequency barcodes that are harder to separate. The first step is to count the frequencies of each barcode using a frequency map, which is essentially a hash table or dictionary. This helps us identify the most frequent barcodes, as these will be the most challenging to distribute without adjacencies. Next, we use a max heap, or priority queue, to manage these frequencies. The max heap allows us to efficiently access the barcode with the highest frequency, which is crucial for constructing the final arrangement. By prioritizing the most frequent barcode, we can ensure that it gets spaced out appropriately in the result array, minimizing conflicts early in the process. The next step is to initialize an empty result array that matches the length of the input barcodes. This array will store the reorganized barcode order. The reason for this is that we need to place barcodes at specific positions, skipping indices when necessary to avoid placing duplicates next to each other. Once the result array is ready, we start filling the even indices, positions like 0, 2, 4, and so on. For each barcode, we extract the one with the highest frequency from the heap, place it at the current even index, decrease its frequency, and push it back into the heap if it still has remaining occurrences. This process ensures that we maximize the distance between repeated barcodes, which is essential for a valid arrangement. After filling the even indices, we proceed to fill the odd indices, positions like 1, 3, 5, and so on, using the same approach. By this point, the even positions have already created spacing, so filling the odd positions ensures there are no conflicts between adjacent barcodes. After placing all the barcodes, the final step is to return the result array. However, if the heap becomes empty during placement or if any barcode's frequency exceeds half the length of the array at any point, it's impossible to reorganize the barcodes without adjacencies. In such cases, we would return an empty list. This is because a barcode appearing more than half the time would inherently force adjacencies, which violates the problem's requirements. The algorithm operates on a few key principles. First, it takes a greedy approach, prioritizing the most frequent barcodes early to ensure they are spaced out as much as possible. Second, the use of a max heap allows efficient extraction and reinsertion of barcodes based on their frequencies. Third, separating barcodes into even and odd indices minimizes the risk of adjacency conflicts. Finally, the algorithm incorporates an implicit early termination check. If a barcode's frequency is too high, it will naturally fail during the placement process. To implement this algorithm effectively, we rely on three main data structures. The first is a frequency map, which counts the occurrences of each barcode. This step operates in O(n) time, where n is the size of the input. The second data structure is a max heap, which helps us efficiently manage barcodes based on their frequencies. Operations like insertion and extraction on the heap take O log k time, where k is the number of unique barcodes. The third data structure is the result array, which stores the reorganized barcodes. This array requires linear space, or O(n), matching the size of the input. Together, these data structures ensure that the algorithm is both time-efficient and space-efficient, making it capable of handling large inputs while maintaining clarity and simplicity in its design. The algorithm's efficiency can be analyzed in terms of time and space complexity. For time complexity, we first spend O(n) to build the frequency map. Then, managing the max heap involves k log k operations, where k is the number of unique barcodes. This includes both inserting the barcodes into the heap and extracting them for placement. The overall time complexity is therefore O(n) plus k log k. For space complexity, we require O(n) for the result array and k for the frequency map and heap, leading to a total space complexity of O(n) plus k. These complexities ensure that the algorithm can handle inputs efficiently, balancing the trade-offs between speed and memory usage. Let's walk through an example to see how the algorithm works in practice. Suppose the input barcodes are 1, 1, 1, 2, 2, 3. First, we build the frequency map, which gives us 1, 3, 2, 2, 3, 1. Next, we insert these frequencies into a max heap, resulting in 3, 1, 2, 2, 1, 3, where the most frequent barcode, 1, has the highest priority. We begin by filling the even indices. Barcode 1 is placed at indices 0, 2, and 4. After each placement, we decrease its frequency, and once it reaches 0, it is removed from the heap. The remaining barcodes in the heap are then used to fill the odd indices. Barcode 2 is placed at indices 1 and 3, and barcode 3 is placed at index 5. At this point, the heap is empty, and the result array is 1, 2, 1, 2, 1, 3. This output satisfies the condition that no two adjacent barcodes are the same, demonstrating the algorithm's effectiveness. Here, we start by importing the necessary modules, counter from the collections module to count the frequency of each barcode, and heap to manage a max heap. In the rearrange barcodes method, the first step is to calculate the frequency of each barcode using counter. This gives us a mapping of barcodes to their respective counts. Next, we use a max heap to store the barcodes, but since Python's heap implements a minute heap by default, we insert the negative of each count to simulate a max heap. For each barcode and its count, we push a tuple of negative count and the barcode into the heap. This ensures that the barcode with the highest frequency will always be at the top of the heap. Now, we initialize an empty list called result to store the reorganized barcodes. The goal is to ensure no two adjacent barcodes are the same, so we continuously pop two barcodes with the highest frequencies from the heap. These are stored as count 1 and count 2 along with their respective barcodes. Both barcodes are appended to the result list, as they are the two most frequent and can be placed next to each other. After using these barcodes, we decrease their counts, and if either still has a remaining count greater than 0, we push it back into the heap with its updated count. If the second barcode also has a remaining count greater than 0, we push it back into the heap as well. This ensures that all barcodes are processed until the heap is empty or contains only one item. Once the loop is complete, we check if there is one barcode left in the heap. If so, we append that last barcode to the result list. This step handles cases where the input contains an odd number of barcodes, ensuring that the final barcode is placed without violating the adjacency condition. Finally, we return the result list, which now contains the barcodes rearranged in the desired order. This implementation efficiently reorganizes the barcodes using a heap to manage frequencies and ensures that the solution adheres to the constraints, making it both optimal and easy to understand. Here, we begin by defining our solution class and the method rearrange barcodes. The goal is to rearrange the barcodes so that no two adjacent elements are the same. First, we count the frequency of each barcode using a hash map. This allows us to track how many times each barcode appears in the input array. Next, we utilize a max heap, implemented with a priority queue, to store the barcodes along with their frequencies. The heap is sorted in descending order of frequency to ensure that the most frequent barcodes are processed first. Then, we initialize an array called result to store the rearranged barcodes and set up an index variable to track positions as we fill in the array. The main part of the logic begins with a loop where we repeatedly remove the two most frequent barcodes from the heap. These will be placed alternately in the result array, ensuring that adjacent elements are not the same. The process continues by placing the second most frequent barcode in the next position of the result array. To maintain the frequency counts, we decrement the counts of both barcodes. If either barcode still has remaining occurrences, it is pushed back into the max heap for further use. This ensures that all barcodes are appropriately placed while respecting the condition of no adjacent duplicates. After processing pairs, if there is only one barcode left in the heap, we append it to the result array at the current index. This handles cases where the total number of barcodes is odd. Finally, we return the result array, which now contains the barcodes reorganized in a valid order. This approach ensures that the solution is both efficient and adheres to the problem's constraints, leveraging the power of heaps to manage the frequency distribution effectively. In this example, we start with the input barcodes 1, 1, 1, 2, 2, 3. First, we calculate the frequency of each barcode using the counter class. This gives us a frequency dictionary where 1 appears 3 times, 2 appears 2 times, and 3 appears once. Next, we construct a max heap to manage these frequencies. Since Python's heap module implements a min heap by default, we store the frequencies as negative values to simulate a max heap. After inserting all the barcode frequency pairs, the heap contains -3, 1, -2, 2, and -1, 3. Now, to reorganize the barcodes, we repeatedly pop the two most frequent barcodes from the heap. For the first iteration, we pop -3, 1, and -2, 2, which correspond to barcodes 1 and 2. These are appended to the result array. Their counts are decrement to -2 and -1, and since they still have remaining counts, we push them back into the heap. At this point, the heap contains -2, 1, -1, 3, and -1, 2, and the result array is 1, 2. Next, we continue reorganizing the barcodes. In the second iteration, we pop -2, 1, and -1, 3, corresponding to barcodes 1 and 3. These are appended to the result array, and their counts are decrement to -1 and 0. Since barcode 3 has no remaining count, it is not pushed back into the heap. The heap now contains -1, 1, and -1, 2, and the result array is 1, 2, 1, 3. In the third iteration, we pop -1, 1, and -1, 2, corresponding to barcodes 1 and 2. These are appended to the result array, and their counts are decrement to 0 and 0. With no remaining counts, the heap becomes empty. The final result array is 1, 2, 1, 3, 1, 2. For the second example, the input barcodes are 7, 7, 7, 8, 8, 9, 9. Counting the frequencies gives us 7 appearing 3 times, and both 8 and 9 appearing 2 times each. We build the max heap, which now contains -3, 7, -2, 8, and -2, 9. To reorganize these barcodes, we follow the same process. In the first iteration, we pop -3, 7, and -2, 8, corresponding to barcodes 7 and 8. These are added to the result array, and their counts are decrement to -2 and -1. Both barcodes are pushed back into the heap. The heap is now -2, 7, -2, 9, and -1, 8, and the result array is 7, 8. In the second iteration, we pop -2, 7, and -2, 9, corresponding to barcodes 7 and 9. These are appended to the result array, and their counts are decrement to -1 and -1. They are pushed back into the heap, which now contains -1, 7, -1, 8, and -1, 9. The result array becomes 7, 8, 7, 9. In the third iteration, we pop -1, 7, and -1, 8, corresponding to barcodes 7 and 8. These are added to the result array, leaving the heap with only -1, 9. Finally, we pop -1, 9, and append 9 to the result array, emptying the heap. The final result is 7, 8, 7, 9, 7, 8, 9. For the third example, the input barcodes are 5, 5, 5, 5, 6, 6, 7. Counting the frequencies gives us 5 appearing 4 times, 6 appearing 2 times, and 7 appearing once. Using these frequencies, we construct the max heap, which contains -4, 5, -2, 6, and -1, 7. To reorganize the barcodes, we begin by popping -4, 5, and -2, 6, corresponding to barcodes 5 and 6. These are appended to the result array, and their counts are decrement to -3 and -1. Both barcodes are pushed back into the heap. The heap now contains -3, 5, -1, 7, and -1, 6, and the result array is 5, 6. In the second iteration, we pop -3, 5, and -1, 7, corresponding to barcodes 5 and 7. These are added to the result array, and their counts are decrement to -2 and 0. Since barcode 7 has no remaining count, it is not pushed back into the heap. The heap now contains -2, 5, and -1, 6, and the result array becomes 5, 6, 5, 7. Continuing the process, we pop -2, 5, and -1, 6 in the third iteration, corresponding to barcodes 5 and 6. These are appended to the result array, and their counts are decrement to -1 and 0. Since barcode 6 has no remaining count, it is not pushed back into the heap. The heap now contains -1, 5, and the result array is 5, 6, 5, 7, 5, 6. Finally, we pop -1, 5, corresponding to barcode 5, and append it to the result array. At this point, the heap is empty, and the final result is 5, 6, 5, 7, 5, 6, 5. In all examples, we ensure that no two adjacent barcodes are the same by always selecting the two most frequent barcodes available at each step. This approach guarantees a valid solution as long as it's possible to reorganize the barcodes. To analyze the time complexity of our solution, we can break it into several key steps. First, we count the frequencies of all barcodes using the counter class. This step involves iterating through the input list of barcodes, which takes n time, where n is the length of the input list. Next, we build a max heap to prioritize barcodes by their frequencies. Each insertion into the heap takes log k time, where k is the number of unique barcodes. Since there are k unique barcodes, this step requires k * log k time in total. Then, in the reorganization step, we repeatedly pop the two most frequent barcodes from the heap. Each pop operation takes log k, and the number of pops is proportional to n, the total number of barcodes. Therefore, the reorganization step requires n * log k time. These steps collectively contribute to the overall time complexity of the solution. In the final step of the algorithm, if there is one barcode left in the heap after all pairs have been processed, we simply append it to the result. This operation is constant time, 1. When we sum up the contributions of all steps, the dominant term is the reorganization step, which takes n * log k time. Considering that k, the number of unique barcodes, is at most n in the worst case, log k is bounded by log n. As a result, the overall time complexity simplifies to n * log n. Shifting our focus to space complexity, the counter object used to store barcode frequencies requires k space, where k is the number of unique barcodes. The max heap, which holds up to k elements, also requires k space. Finally, the result list, which stores all n barcodes, requires n space. These components determine the overall space usage of the algorithm. Combining the space requirements, the total space complexity is dominated by the counter, heap, and result list, giving us n plus k overall. In the worst case, where all barcodes are unique, k equals n, and the space complexity simplifies to n. To better understand the algorithm's performance, we can analyze the best, average, and worst cases. In the best case, where all barcodes are identical, k equals 1. The heap operations are minimal, and the time complexity reduces to n. For a typical distribution of barcodes, the time complexity is n * log k. In the worst case, where all barcodes are unique, k equals n, and the time complexity becomes O, n asterisk log n. Comparing this to a brute force approach, where we generate all permutations of the barcodes and check each one, the difference is stark. A brute force solution would take O, n, time in the worst case. By leveraging a max heap to construct a valid arrangement greedily, we significantly reduce the complexity to O, n asterisk log n, making this approach highly efficient. Finally, let's solidify our understanding with a mathematical proof of the big O bounds. The heap operations govern the time complexity, which is O, n asterisk log k. Since k is always less than or equal to n, log k is always less than or equal to log n. This allows us to conclude that O, n asterisk log k, is equivalent to O, n asterisk log n in the worst case. For space complexity, the combined contributions of the counter, heap, and result list amount to O, n plus k. When k reaches its upper limit, equaling n, the space complexity simplifies to O, n. With these bounds, we can confidently say that the algorithm is optimal for this problem given the constraints. It efficiently balances time and space complexity while ensuring correctness. When solving distant barcodes, there are some common mistakes to watch out for. One frequent issue is relying on a brute force approach, where all permutations of the array are generated. This method has factorial time complexity, or O, n, which becomes computationally infeasible as the input size grows. Since the problem explicitly requires an efficient solution, brute force is not a viable option. Another mistake is neglecting edge cases, such as when all elements are identical or when there's an uneven frequency distribution, like 1, 1, 1, 2. Overlooking these scenarios can lead to incorrect outputs or runtime errors. Finally, some solutions ignore the constraints imposed by the frequencies of the barcodes. For example, the most frequent barcode may exceed the allowable distribution limit, making it impossible to rearrange the array while avoiding adjacent duplicates. Failing to account for this can result in invalid solutions or infinite loops in your implementation. Another area where mistakes often occur is in the implementation details, such as sorting or using a priority queue. If the logic for managing the most frequent elements is flawed, it can result in suboptimal arrangements where adjacent duplicates remain. This undermines the purpose of the solution. Additionally, overcomplicating the implementation is a common pitfall. Some solutions introduce unnecessary data structures or extra steps, which increase both time and space complexity. However, the problem can often be solved more efficiently using a simpler approach, such as a greedy algorithm combined with a heap. Avoiding these extra complexities leads to a cleaner and more performant solution. To perform well in interviews, it's essential to grasp the key insights of this problem. At its core, it boils down to frequency counting and a greedy reordering strategy. Understanding the relationship between the most frequent barcode and the total number of elements is crucial to crafting a valid solution. Many adjacency constraint problems, including this one, often rely on heaps or sorting to control the placement of elements. It's also important to validate your solution against edge cases, such as arrays where all elements are the same, cases with one element appearing far more frequently than others, or inputs that are already valid with no adjacent duplicates. From an optimization perspective, a heap-based solution offers a good balance of efficiency and clarity, running in O, n log k, where k is the number of unique elements. This makes it well suited for handling large inputs. This problem has a lot in common with other well-known LeetCode problems. For example, LeetCode 621, Task Scheduler, also involves adjacency constraints and requires frequency counting combined with a greedy scheduling approach. Similarly, LeetCode 767, Reorganize String, is a direct analog to this problem, where characters replace barcodes, but the adjacency requirement remains. Another related problem is LeetCode 358, Rearrange String k distance apart, which generalizes the adjacency constraint by requiring elements to be at least k distance apart. And of course, LeetCode 1054, Distant Barcodes, is the problem we're working on and focuses specifically on barcodes and their adjacency restrictions. Together, these problems highlight a recurring theme of using greedy algorithms and data structures like heaps to meet adjacency constraints efficiently. There are several alternative approaches to solving this problem, each with its own trade-offs. One popular method is a heap-based greedy algorithm, where a max heap prioritizes the most frequent elements, and they are alternated to avoid adjacency. This approach is efficient, with a time complexity of O(n) log k, but it does require additional space for the heap. Another option is bucket sort with greedy placement, where elements are sorted by frequency and strategically placed into specific slots to prevent duplicates. This method is even faster, with a time complexity of O(n), but it can be harder to implement and debug. Finally, a two-pointer approach can be used for simpler variations of the problem. This method allows for in-place reordering of elements, but it's less intuitive and has limited applicability when adjacency constraints are more complex. Each of these techniques has its strengths and weaknesses, so the choice depends on the specific requirements of the problem. Great job making it to the end. In summary, we used a greedy approach to solve the distant barcodes problem, achieving an efficient solution with O(n) log n time complexity. The key takeaway is the importance of combining heap-based strategies with greedy placement. Thanks for watching, and don't forget to keep practicing and exploring new problems. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!